Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today we're diving deep into a fascinating blog post about simulating water over terrain in games. It's a surprisingly complex topic, but the author presents a really elegant solution. Let's get started.
I'm eager to hear this. The title alone sounds challenging. What's the core problem the author tackles?
The core issue is creating realistic-looking and computationally efficient water simulation for a game, specifically one with terrain modification. Many games avoid this complexity, but the author's game requires it. Think digging, mining, and terraforming, all impacting water flow.
So, no simple water below a certain height trick? That's what I'd expect in a simpler game.
Exactly. The author dismisses those simplistic approaches as boring and dumb. He wants something more dynamic, more believable. He explored complex fluid dynamics models initially, but they were too computationally expensive for his game. That's where the virtual pipes method comes in.
Virtual pipes? That sounds intriguing. Is it some kind of approximation?
Yes, it's a clever approximation. Instead of directly simulating water velocity, the model tracks water flow between grid cells, like water flowing through imaginary pipes connecting the cells. It's a staggered grid approach, meaning water height and flow are stored at different locations on the grid for better stability.
Staggered grids. I've heard of those. They avoid some of the instability issues of collocated grids, right?
Precisely. Collocated grids can lead to unrealistic zero-velocity situations, even when water is clearly flowing. Staggered grids elegantly solve that. The virtual pipes method uses three arrays: water height, horizontal flow, and vertical flow. This simulation then involves three steps: flow acceleration, outflow scaling, and water column updating.
And what about terrain? How does that factor into the virtual pipes?
Brilliantly simple. The terrain elevation is simply added to the water height when calculating flow acceleration. So, if a cell has higher terrain, its effective water height is higher, causing water to flow downhill. It's a very intuitive integration.
That's elegant. But what about the stability of the simulation? Fluid dynamics can be notoriously unstable.
The author addresses this with outflow scaling. This step prevents negative water amounts by scaling down outgoing flows if they exceed the available water in a cell. It's a crucial step for maintaining stability. He also mentions the Courant-Friedrichs-Lewy (CFL) condition, which helps determine a suitable time step to prevent instability.
So it's a balance between accuracy and computational cost. What are the limitations of this virtual pipes method?
The author acknowledges limitations. The model lacks inertia and velocity diffusion, meaning fast-moving water might not behave entirely realistically when encountering obstacles or other water bodies. It's a simplification, but a very effective one for the intended purpose.
He also mentions using this on triangular grids, right? That's a less common choice for game development.
Yes. His game uses a triangular grid, and he adapts the virtual pipes method to that grid structure as well. It's a more complex implementation, but it shows the flexibility of the core approach. It's a testament to the elegance of the method.
This is fascinating. It's amazing how a relatively simple model can achieve such realistic-looking results. Thanks for summarizing this.
My pleasure. It's a great example of clever game development techniques. And that's all the time we have for today's Tech Bytes and News. Join us tomorrow for another deep dive into the world of technology. Goodbye.
Bye-bye.